Thank you. So today I want to finish discussion of the algorithm for recognizing unknots and talk about a couple of other algorithms also. So we'll do a little bit of three-dimensional manifold theory, not too much, but a little bit. And then my plan is to then talk about the recognition problem for the three-sphere, which involves some new ideas connecting algorithms and computational complexity to differential geometry and minimal surface theory. So I want to talk about that and some more about complexity theory for the rest of the time. But first, I sort of think that I should go through some of the details and issues that come up when you actually go into the heart of this algorithm for recognizing the unknot. After Haken published it, it probably it didn't get very much attention, for not as much as it should have, because people thought it was extremely difficult. But it's been simplified repeatedly, and it's still being simplified. I'm going to show you a couple of new simplifications today. So I think it's actually quite approachable today, but there are some issues in three-manifold topology that are a little more difficult than those that arise for curves on surfaces. So last time we discussed what a normal curve on a surface is, and then we just ended by defining what a normal surface is in a three-dimensional manifold. And the definition was that if you look at any single tetrahedra in a triangulation, the surface must intersect it in a collection of disks, each one of which has one of these 7 types. There's 4 types of triangle disk that you can cut across the tetrahedron with, 1 near each corner. And there's 3 types of quadrilaterals. And the right way to think about the quadrilaterals is that they split the 4 vertices into pairs in 3 different ways. So one important fact that comes up, and I'll come back to this, is that you can only actually have one of these 3 quadrilaterals in a tetrahedron, because if you had 2 different types, they would be forced to intersect. And we're only working with embedded surfaces. I should have maybe emphasized that. The theory of normal surfaces describes embedded surfaces. It does not describe immersed surfaces. And it's an interesting question as to why. We'll see that in a minute. So these are just indicating how these quadrilaterals separate the 4 vertices in 3 different ways. So just as with curves, we can associate vectors to these normal surfaces, which count how many of each disk type they have. So for the example here, we see this particular vector. There's going to be 7 coordinates for every tetrahedron, because there's 7 possible disk types. And this integer vector will just count how many of each disk type there is. So here we see there's 1 quadrilateral. That's counted by the 5th entry, the red one over there. The first one refers to the triangle in the far left corner. Of course, the ordering is pretty arbitrary, but there's always going to be 7 entries for every tetrahedron, and this vector, integer vector, will completely determine how this tetrahedron intersects a given surface. Now, of course, that wouldn't be true if the surface itself was not embedded, right? If these triangles were allowed to cross each other, there'd be many configurations with the same vectors. So we're using in a strong way that we're working with embedded surfaces. So let me talk about these quadrilaterals a little. It turns out that the quadrilaterals are a big source of irritation, I would say, with this theory. They cause a bookkeeping issue. When you start to work with vectors of different types, you want to make sure you don't introduce 2 different types of quadrilaterals, which would stop you from having intersecting surfaces. And there's a simple way to do this. If I have tetrahedra, I can just break my problem into 3 to the t problems, exponentially many problems. In each problem, I'm only going to allow 1 type of quadrilateral in each tetrahedron. Right? So I have 3 choices for every tetrahedron, t tetrahedron. So there's 3 to the t choices. So that's an exponential number of choices. But it turns out once I make that choice, the problem becomes polynomial. So all the exponential difficulty is tied up with these quadrilaterals. We'd have a nice polynomial time algorithm for unknotting if we could figure out how to choose these quadrilaterals properly in advance. So this was an observation of Haken. The reason that it reduces to polynomial time is because it becomes a real linear programming problem after you choose these quadrilateral types. You can just take the real function, which is the Euler characteristic of a normal surface, and maximize it, and it turns out that that will give you a solution to the process is called normalization. And just with curves, we could take any curve at all and isotope it to become normal. So we can do similar things with many classes of surfaces. So how do we start with an arbitrary surface and turn it into one that intersects any one of these tetrahedrons, these triangles or quadrilaterals? Methods that are used all the time in 3-manifold topology. So if you're familiar with them, you could just sit down and work this out quite easily. But I'll show you these. They're not very hard. The theorem says that if we have 3 operations, one is isotopy. We just push the surface around inside the 3-manifold. Another one is compression. So compression is what you see with that left hand, the little circle there. You take a little disk, which has its boundary on the surface, and you just squeeze off the neck, cutting the surface up into 2 pieces there. I'll show you some more pictures in a minute. And there's also a sort of operation like that at the boundary. So this big rectangle there is supposed to be the boundary of the 3-manifold, in case our manifold has some boundary. And then parts of the surface may bound a half disk like that with the boundary, and you can just chop along that half disk, and that's called the boundary compression. So here are pictures of compression along disks. Locally splits up the surface into 2 pieces, and boundary compressions does the same thing near the boundary. So with these operations, isotopy, compression, boundary compression, we can make any surface at all into a normal surface. The one thing we have to be careful about is a surface may have a component that lies entirely within a tetrahedron. Then we can't do anything. Well, we can compress it if we want, and we can just make it disappear to a point. So we'll ignore little components that lie inside a tetrahedron. So what's the process? How do you get these potentially very nasty surfaces to deform to these triangles? So what we do is let's fix our attention on one tetrahedron and look at how this surface intersects the boundary face, the 4 boundary faces. And here I've assumed that one of the boundaries of this tetrahedron, the bottom triangle, actually lies on the boundary of the manifold. So we see a surface with boundary here. So we see both a compression and a boundary compression can be done on that picture. We can take that little circle of intersection there, do a compression, and split off a 2-sphere, and split off a disk at the bottom. And by doing that, we reduce the number of intersections with the boundary of the tetrahedron. So we'll get a simpler set of intersections. And inside the tetrahedron, you can now isotope that triangle to look nice. And the claim is that by doing a sequence of such simplifications, we'll always be able to reduce all the way to these nice pictures. Let's see a couple more cases just to see some of the complications that might come up. So I just showed the simplest case last time. An actual surface may have many components of intersections. You can have circles inside circles, and half circles, circles inside half circles, and all kinds of things. But there's a simple procedure, inductive procedure, to simplify these pictures. So first you look just inside a triangular face. And you look for a circle that lies completely inside that triangular face. And there may be many. So if there's many, you look for one that's innermost, that doesn't have any inside it. Okay, so you can order them. And there always will be an innermost one, because there's a finite number. And you take one of those innermost ones and do a compression on it. Right? We're allowed to compress. The compression may be trivial in that it may split off a little two-sphere, but that's fine. You'll reduce the number of intersections with the triangular faces. And eventually you'll have none. So you can get rid of these circles of intersection quite easily. Yes, question?
What's the difference between the top simplification and the bottom one here?
Let's see. Maybe I just did it twice so you'd really pay attention. I think I was, yeah. You're pointing out that some of these slides were prepared fairly recently. Yeah. So you can do something similar with boundary compressions, but there's something else you need to do. So let's say we've eliminated all those circles of intersection with the triangular faces. We now may have, we're not yet at a normal surface because we may have, for example, arcs of intersection that double back on a triangular face and hit an edge twice. Well, if we see one of those, we can just isotope it across that edge. I've sort of indicated that picture over here. You can push that surface across that edge, and when you do that, you get rid of one of these doubling back arcs, and you reduce the number of closed circles with a face, closed loops with a face, or we're reducing the number of intersections with the edges. And we do. It's not too hard to make this precise and make sure that you always make progress. You can see some things we have to worry about. Here's a loop on a face. Here's an arc on a face that loops back. It may have a little circle blocking it from going out. But if we've gotten rid of all the circles, then there aren't going to be any of those loops that are getting in the way. One problem is that when we push across the boundary, we may create loops in some other face. But there's a simple complexity which tells you you're always making progress. So this process stops. Yes? Question? So the question is the normal surface obtained unique? Well, so I've defined, certainly not the way I've defined it. It could be, it's not going to be unique in this, because you could do things in different order and potentially cancel things differently.
So what's the goal? To simplify it to a normal surface such that...
Right, so right now I'm just saying that you can get a normal surface. Later we'll see that, for example, if there's an unknotting disk, then there's a normal unknotting disk. Okay, so it will reduce our search for an arbitrary disk, which is, an arbitrary disk can be very complicated, right? You can think of it winding around the whole town or something, but once it's a normal disk, we'll know where to look for it. So it'll be subject to algorithmic procedures. Yes, question?
Which topological invariants remain the same?
Which?
Are there any topological invariants that remain the same surface?
As we move it around? Well, for example, if we start with a disk and do these procedures, we'll never increase the genus. Right? The isotopy procedures and the compression procedures, we may split off two spheres, but we'll always have a component that's a disk if we start with a disk. So what we're going to see today is that for the kind of surfaces that we're interested in algorithmic topology, things like two spheres that non-trivially split things up and disks that bound a knot or that give a compression, these moves don't mess up those properties. They preserve those properties. So it suffices to search for those properties among the normal surfaces. Other questions? Yes?
And do you think it's possible to get a normal surface that is isotopy to the original surface?
Right, so the question was, can we just do isotopy? So that was the way people originally did it. That was the way they originally did this problem. This is much simpler because I don't have to worry. When I see a circle, I just say compress it and it's gone, right? If you want to get rid of it by an isotopy, you have to make sure it bounds a disk on one side and that you can isotope that disk across that face. Well, often with the right hypothesis, that will be true, and that was the way these problems were originally set up. But it's just easier to follow the argument this way. But you certainly can do it in a lot of cases just by isotopy. Okay, so there's one more case. You may have thought that having gotten rid of all these looping back and closed loops in faces, you might have thought we were already normal, but we weren't yet. And these are examples of other surfaces which are not normal. They intersect the tetrahedron not in disks, not in triangles or quadrilaterals, but they have the property that if you look at any triangle, you're not going to be able to, if you just look at a triangular face on the boundary, it looks just like the intersection with a triangle or a quadrilateral. It just has these arcs going between distinct edges. There's no loops and there's no half loops. But these are not normal disks. So what property do they have that we can try to get rid of? Well, each of them has the property that they intersect. So each of these surfaces has the property that they intersect an edge of the tetrahedron in more than one point. Right? So if we look at the lower left here, the front edge of the tetrahedron intersects this dotted surface in 2 points. And in fact, I can isotope that surface across that edge and reduce the number of intersections with the edges by 2. And you can always do that if you have a surface intersecting with intersecting an edge in more than 2 points. So that's not a very hard argument, but I won't give it. And so we do all three of these operations: isotopy, compression, boundary compression, and pushing across an edge where there's excess intersection, more than one point of intersection. And in the end, what we'll get is a normal surface. Okay, but we have changed the surface, so if I'm going to make any claims about what I get at the end, I'm going to have to make sure that I haven't messed up the properties I want, the properties that I started with. So at the end, what we get is a surface which intersects each tetrahedron in some disk. It can't be of higher genus because I can compress away higher genus. So it'll intersect each tetrahedron in a disk, and that disk will not cross any edge more than once. So the triangles cross 3 of the edges, the quadrilaterals cross 4 of the edges. It turns out there isn't any disk that crosses each of the edges once, right? So that's an exercise. So those are all of the disks that can be left over, and those are exactly the normal disks.
What did you do with the surfaces that are inside?
I'll just ignore them or erase them. They're trivial and they won't matter for anything we do. You can just remove them. Okay, so since Jeff gave us some algorithm theory this morning, I'm going to give you a little we're going to take 10 minutes for some 3-manifold theory. So this is the origins of normal surface, which were discovered by Kneser and introduced by Kneser in the 30s. And Kneser used them to prove that 3 manifolds had prime decompositions. So I want to show you how this argument goes. We know everything we need at this point to prove this. So this was before Haken, so we don't need the connection to integer linear programming. We just need the fact that surfaces can be deformed to be normal in the way I just showed you. So you start with a 3-manifold, and you cut it along spheres, and you get these pieces, M1, M2, M3, M4, and M5, and so on. And you say that the original manifold, these are closed orientable manifolds, you say that the original manifold is a connect sum of these 5 pieces. And it was natural to study these prime manifolds because they seem to be the simplest type of 3 manifolds, and it certainly looked like everything was built from unions from these connect sums of things that were prime. But the question arose, and it's not so obvious, how do you know you can't take a 3-manifold like the 3 torus and somehow put a sphere in it and cut it up into 2 pieces, and then the 2 pieces, perhaps each of them can be cut up into 2 more pieces and along spheres, and always in a non-trivial way. So if you take a 2-sphere that bounds a 3-ball and try to do this connect sum, you'll just get the original manifold back again. Let me say a little more precisely what connect sum means. You start with 2 closed 3-manifolds. The connect sum is gotten by removing a ball from each of them and gluing the 2 spheres together. So you get a closed 3-manifold. And so here's a little exercise. How many ways are there to do that? Was that well defined, what I just said? So if we think about whether that's well defined, we have to think, how many ways are there to glue a 2-sphere to a 2-sphere? And it turns out there's 2, right? There's 2 orientations for a 2-sphere. There's unique diffeomorphism in each orientation class. So you have to have a rule that specifies the orientations in order to get this to be well defined. But anyway, you have this process of connect sum, and the question is, how do you know how do you know this makes sense? How do you know it doesn't keep going forever? Maybe manifolds are like the rationals, where you can write things as products of infinitely many, or sums of infinitely many pieces, rather than like the integers. And this is sort of a picture of different ways we can think about connect sum. The easiest way to think about it is laid out left to right. You take all these manifolds and add them successively by removing balls and adding the next piece. But you don't have to do it that way. So this shows up even in 2 dimensions. If you think of cutting a surface up into handles, you can lay the surface out, and then you'll see these 4 circles that cut it up into punctured tori. But if you lay it out differently, you can get more circles, no 2 of which are parallel on the surface. So the number of connect sums, the point of this picture is it's not quite the same as the number of non-parallel 2-spheres, although they're closely related. You have to be a little careful about how the 2 spheres that cut up a manifold are connected to the number of summons. So Kneser showed that you always have a finite decomposition. There's a maximal number of prime pieces that any compact 3-manifold can be cut into. Prime 3-manifold is one that can't be cut into any pieces. And so this means lots of 3-manifolds are prime. All the ones that you get stuck on when you take the maximal set must be prime. Being prime is equivalent to the property that every 2-sphere bounds a ball, with 2 exceptions. Well, one orientable exception, which is S1 cross S2. But that's not an important point for us. So let's just take 5 minutes to go through the proof. This will be too fast to follow, but let me just show you anyway how normal surfaces play a sort of a nice role in this argument of the finiteness of connect sums. This was one of the main theorems in 3 manifolds pre-60s, I guess. So what we're going to do is look for a lot of two spheres that are non-parallel. If there's a connect sum into k pieces, then we have at least k minus 1 non-parallel two spheres. So what Kneser said is, let's show you can't have too many non-parallel two spheres. Then we'll get a bound on how many connect summons there can be. And how will we stop there from being a lot of non-parallel two spheres? We'll take a collection of two spheres. We'll make them normal all at the same time. And then we'll show that there can't be too many non-parallel normal spheres. So that's the scheme. So let's say that a collection of two spheres is independent if no pair is parallel. We can also add in another condition. That's going to be enough for us, I think. But we can add in another condition that no subset bounds a ball. So no pair looks like the spheres at the left or the four spheres at the right. Those don't contribute to the number of connect summons if they sit inside a manifold like that. Anyway, let's suppose we have such a collection of two spheres. And we can ask, how big can that collection be? And Kneser showed that the number is at most 7t minus 1. So if we triangulate the two sphere with t tetrahedra, then the largest number of two spheres we could possibly have is 7t minus 1. Now, Kneser's original argument was a little more complicated than the one I'm going to give you because he used some homology and so on. We won't need that. We'll reduce it to three little lemmas. First, we'll show that if you have t tetrahedra, then you can't have more than 7t non-parallel two spheres. If you have 7t plus 1 normal two spheres, then two of them will be parallel. Or 7t plus 1 two spheres in general, normal or not, then two of them will be parallel. The second thing we'll show is that we'll show that by making those spheres normal and showing there's at most 7t normal two spheres, none of which are parallel. And then we'll show if you, well, all right, so that will be enough for these tetrahedras. So this is the picture that gives the idea of Kneser's argument. You have these, this collection of two spheres running through this tetrahedra, and maybe there's far more than we want. Maybe there's 1,000t. We're going to show that at most 7t of these are non-parallel. And you can see that there's some hope for this because as they cross this tetrahedra, most of these surfaces are parallel. Right? There's a lot of parallel triangles. There's a lot of parallel quadrilaterals. In fact, if my two spheres were made entirely of those green pieces over there, you see what I've done here? I've got here a tetrahedra with 4 triangle types and 1 quadrilateral type. And if you look at the parallel ones, the ones that are in the middle are all colored green, and the ones that are on the edges of that stack of parallel disks are colored red or blue. If my two sphere was made entirely of green pieces, then it would have to be parallel to another two sphere. Right? Because let's say you're on one of the, let's say you're a two sphere, okay? Think of yourself as a two sphere, and you're in one of these tetrahedra, and you're a green triangle in that tetrahedra. Well, if you look to your right, you see something parallel, and if you look to your left, you see something parallel. So if you're made entirely of green triangles and quadrilaterals, then you'll always see something on your right and something on your left. You'll be parallel to another two-sphere on both sides. If you're not parallel on both sides to another two-sphere, you must have one of these red triangles or quadrilaterals somewhere in your triangulation, or you must have one of the blue ones. Now, the blue ones come from neighborhoods of vertices. If I take a neighborhood of a vertex, I get a little sphere called a vertex linking sphere. Right? So we can ignore the blue ones. How many red pieces are there in this tetrahedron? Okay, so that's the next exercise. How many red pieces are there in a tetrahedron? Yeah?
Can you just explain why the blue ones are not important again, please?
Excuse me?
Can you please explain why the blue ones are not important?
Yes, because I'm going to take a maximal family of two spheres, normal two spheres, because I want to count how big it can be. So one kind of two sphere I'll get is a neighborhood of a vertex. So I'll get a little triangle for around every corner of a tetrahedron that comes to, and those will be the blue ones. Those are not going to be, those are all going to be trivial, so I'm going to forget about them. But the red ones maybe are non-trivial. How many red pieces are there in this tetrahedron? Six. All right. There's 6 red pieces, and there can't be more than 6, no matter how many of these different types of surfaces I have. I never have more than 6 red pieces in any tetrahedron. So that means I have at most 60 red faces in all of the manifold. And if a sphere doesn't have one of those 60, then it's parallel to another sphere. So you put that together, you see that we can have at most 6T normal two spheres, no pair of which is parallel. In addition to it turns out you can have as many as T vertex linking spheres. So altogether, the most you could have is 7T. So it's a very elementary argument, just a little counting argument by saying that if a sphere is not parallel, it must be non-parallel in one of these tetrahedra, and then it must have one of these red faces, and you can count how many there are. Okay, so we can count how many disjoint normal surfaces that there are that way. There's at most 60 normal spheres that are disjoint, but maybe in the connect sum we have non-normal spheres. So we have to make sure that when we take a collection of spheres and do this process of normalization, we have at least as many normal two spheres at the end, there's no two of which are parallel, as we started with. So the logic is, supposing we start with a lot of non-parallel two spheres, we normalize them by this compression, boundary compression, and isotopy. At the end, we want to make sure we still have just as many normal two spheres. And if that's bigger than 6T, we'll get a contradiction. And that's what this sort of picture illustrates. Isotopy doesn't change whether the spheres are parallel or not, so that's not going to be an issue. The only operation we have to worry about is the compression operation. And as indicated in this picture, if you start with a sphere that if you start with a family of spheres that are independent and compress one of them, you'll get an extra sphere, which and now you may have to throw away one of the two spheres you get, but you'll still get an independent family by keeping one of the two spheres that you get. So you won't decrease the number of independent two spheres. So that very rushed was Knese's prime decomposition theorem. And this was one of the basic theorems about three manifolds until certainly until the mid-50s. Okay, so that was an application of normal surfaces to three manifold theory. It turns out that a lot of the things that we're developing, that have been developed to study algorithms using normal surfaces have also had implications to three-manifold theory. But I'm not going to talk about that so much. So now I'd like to go through some of the details of how to do an unknotting algorithm using normal surfaces.
Question?
Yes?
If you, I wonder how the 70 value is tight, because...
It's not at all tight, yeah. You can get it to 2t, actually, if you're a little more careful.
Because if you try a relatively number of t trigra, so it seems that you should get a smaller fraction of the...
Yeah, you can do, at least for spheres and for spheres, you can get it down to 2t because, for example, one of these red guys must connect. If you look, some of these boundary regions in the faces of the tetrahedra are hexagons, and they connect to hexagons on the other side. So these red guys actually come in triples in simplicial complexes. So you can divide by 3 just by that observation. But the important thing is just that it's a linear bound for. It's generally not, even the best you can do is not going to be tight. In fact, I had a student who worked out that it is tight for connect sums of L3-1 or something, but it's not going to be close to tight with certain triangulations. In general, it's not going to be close to tight. So let's do this unknotting. So we're given some kind of a curve in the plane, or maybe a polygon in R3, and we want to test to see if it's the unknot. So the first thing we have to do, or we're going to do, is set it up so that that curve lies on the one skeleton of a triangulation of the 3-sphere. So to make a triangulation of the 3-sphere, we start with one very big tetrahedron containing the knot. So the outside of that gives us a tetrahedron in S3. That's going to be one of our tetrahedra. And then we're going to subdivide that a lot to get the knot to lie on the one skeleton. And then the idea is to remove a neighborhood of the knot. We're going to turn this into a 3-manifold problem where we use normal surface theory. So we're going to remove a neighborhood of the knot and get a 3-manifold with torus boundary and ask, is that 3-manifold a solid torus? So this knot manifold, the complement of the knot in S3, is a solid torus, and the knot is trivial if and only if this boundary torus, this peripheral torus, the torus that's a neighborhood of the knot, the removed knot, if that's a compressible torus, if there's some disk, like this red disk, that fills in that torus. So it's sort of interesting to try and do this as efficiently as you can. There's a lot of algorithms, pre-existing algorithms, involved in this step of setting up this. For example, you want to take a curve in the plane and say that it can be, take a knot diagram and say it can be realized with straight edges. How many straight edges do you need? And then you sort of form prisms over the crossings and subdivide. And so from the point of view of existence of an algorithm, the only thing that matters is that you can do this in some computable time. But it's interesting to try and get this number as small as possible. The estimate that we gave, and it becomes important for complexity purposes, the construction we gave showed that you could do this in n log n time, and you wound up with 253,440 times n plus 1 tetrahedra. So the trefoil required over 750,000 tetrahedra by this process. And that was that was just in S3. That was for knots in S3. For knots in a manifold, it's even more complicated.
So combinatorial means the knot is an element.
Right. So this a combinatorial triangulation is one where the link of every face is a sphere. So it's a nice manifold triangulation. We want one that also has properties like, well, for example, if you took an annulus, you could have a perfectly good triangulation of the annulus that looks something like this. This would be a fine combinatorial triangulation of an annulus. But you can't, in this kind of triangulation, you can't take a regular neighborhood of that boundary circle. So we want to be able to take regular neighborhoods of curves on the boundary. So we had to do some more subdivision. Once we have this nice triangulation of the knot complement, we look for a compressing disk. We look for a disk that lies on the boundary torus and is embedded inside the complement. So we again now go to what we did with curves. We'll assign a vector, an integer vector, to each tetrahedron, to each surface rather. It'll have 7 coordinates in every tetrahedron. And this gives a description of a surface by measuring how that surface cuts across the tetrahedron. It's a very efficient tetrahedron, very efficient surface description, exponentially more efficient than one that keeps track of vertices of a surface. And then given a knot, a disk that spans the knot, that certifies that it's a non-knot, will be given by some integer vector with 7t coordinates. And just like before, there's some conditions on these. There's some conditions on the integers you get from these vectors. Namely, when you have 2 adjacent tetrahedra, they have the surfaces in each one, the normal surfaces in each one, have to match up along the common triangular face. So let's see a little example here. We have a tetrahedron on the left, which has 1 quadrilateral and 1 triangle, both of whom have parallel edges on that face. So we see 2 types of disk, 1 quadrilateral and 1 triangle, give rise to this type of edge on the triangle. From the tetrahedron on the right, we also have 2 triangles with that type of edge. And when you glue together that face, those will close up and not leave any dangling boundary. So the kind of equations that gives is exactly the same as before. It's Vi plus Vj equals Vk plus Vl. Linear equations of a very simple type. This time we have a vector with 7t coordinates. There's 7t variables. The number of equations is 3t over 2 because we get 3 equations for every, let's see, is it 3t over 2? Each face gives us 3 equations, and there's 4 faces on a tetrahedron, so that's 12t equations, but each one occurs twice because faces meet 2 tetrahedrons. So it should be 6t equations, not 3t over 2. 3t over 2 was for curves. It should be 6t for surfaces, and then there's an inequality that says that each one of those is greater or equal to 0. So we can add vectors, and we can again look at what the geometric property is that corresponds to adding vectors. So here's a simple example. This is called the Haken sum operation. If we have 2 normal surfaces, one intersects in a green triangle and one in a red triangle, so adding the vectors is pretty easy. They're the same triangle type, so you just get 1 plus 1 equals 2. The geometric sum, if they're disjoint, you just take the disjoint union. But if they intersect, then you do a cut and paste along the intersection arc. And there's two ways to cut and paste, and there's always exactly one way that gives a normal surface as the output. If you did the other way of cutting and pasting, which I've done here, then you'll get an irregular sum, and you will not get, you see that at the left. At the right is the regular sum, the Haken sum. At the left is the irregular sum, the wrong way to do it. And if you do that, you'll see you get these pieces that are not parts of normal surfaces. So you have to check all the cases. There's different ways the two quadrilaterals can intersect of the same type. Two triangles can intersect. Different types of triangles can intersect. In all cases, there's exactly one choice that gives a normal surface. Any questions? So we have this geometric sum that corresponds to so you missed your chance to.
So should I ask about quadrilaterals?
Yeah. Yeah. Okay. Okay, so maybe I should stop for a couple of minutes and ask you to think about what's the question that Sol sort of asked about quadrilaterals? There's an issue with intersecting quadrilaterals. If we had quadrilaterals of different types, then there's no way to take their sum to get a normal surface. And this is something that a lot of people have made efforts to get around to try to handle immersed normal surface theory. But it's a big drawback so far that hasn't been addressed. If you could really handle immersed normal surface theory in the same way we have embedded normal surface theory, we could solve problems like the word problem in three manifolds and so on. Yes?
I was wondering if you would take a short break.
Okay, let's take a short break. Hey, well, does anybody have questions while we take a short break?
So Haken's inspiration for this was what?
Yeah, that I don't know.
It's a little crazy. It's not at all obvious that this turns out to work, because there's other types of normal surface positioning you can try. For example, you could take knot diagrams and try and put surfaces in canonical position relative to the diagrams. And there's many other things you could do besides this type of picture. And in many of them, these corresponding facts are not true. The geometric addition doesn't correspond to vector addition. So it's not automatic that this turns out to be true. Haken himself actually did not define normal surfaces quite this way. He used the dual formulation, which is a little harder to visualize, but this is what people use today. Okay, that's enough for a break, I think. So under this geometric or algebraic sum, which coincide, there's another series of nice coincidences. First of all, Euler characteristic works very nicely. Euler characteristic, if you take the sum of two surfaces, their Euler characteristics add. And that's very simple. It's because this operation just cuts and pastes, but doesn't change the number of vertices, edges, or triangles.
So Euler characteristic is compatible with addition. And so is weight. Weight, remember, the weight of a surface is how many times it intersects the edges of the triangulation. And again, this geometric process does not change that. So it is preserved by addition. And those are two very useful facts. So now let's go on to finish off the algorithm for unknotting. We have all the tools now. There's one little lemma I still have to prove. So what's the idea? We're going to, instead of working directly with unknotting, we're going to reduce it to one of two other problems. Or we're going to show that it follows from one of two other problems. One is the boundary compressible problem. That's the one we've been talking about, where you remove a neighborhood of the knot and get the exterior of the knot and ask, is that a compressible three-manifold? And the other one, which is also implies unknotting, is called the split link problem. So this is where you take a link with two components and ask whether you can just move them apart. Move them apart so you can separate them by a plane or two. So we can decide only to look for solutions that meet the boundary exactly along disks that wind around this annulus monotonically. So just to be a little more precise, if a tetrahedron is interior to the manifold, we don't restrict what kind of disk types we allow. So the green ones are allowed. There's a quadrilateral that's allowed as well that I didn't draw. But if a tetrahedron meets the boundary, I'm going to allow the interior triangle at the top, and I'm not going to allow those two red triangles. I will allow the green triangle that runs along this way. And in this way, you can eliminate all the boundary. I'm going to allow that quadrilateral and that quadrilateral as well. And in this way, we can eliminate this problem of potentially finding a trivial two-disk. Because any two-disk which is made of these green pieces must have boundary a multiple of a longitude, which implies that it gives an unknotting disk. But there's an even better way to avoid all these technicalities, which is to avoid boundaries altogether. We're just going to ask the question, is a certain link split? And that will imply a solution to unknotting. So let me show you how this logic goes. It's very simple. If you take an unknot, so look at the red unknot there, and you push off a copy to one side, then you get a trivial link. You get an unlink of two components, and you can separate those two components by a two-sphere, right? So if a knot is unknotted, its push-off gives you a splittable two-link. But if you have a curve that is knotted and you push off a copy of it, you will never get a split link.
Why?
Longitudinal framing. There are many ways to
But
framing.
you have to. Well, it doesn't matter how you push off. You'll never get it with any framing if it's not the if it's a knotted curve. But in particular, with the unknot, you will get a link if you push off with some twists. You have to be careful to push off in the right way. So here's the argument that you will never get the unknot if you take a push off of a knotted curve. You'll never get a split link, rather. You'll never be able to fit a two-sphere between these two components. Suppose we could fit a two-sphere between these two components. Now, these two components have an annulus running between them, right? We've just taken a copy of the knot and we've pushed it off in one direction. So there's a little annulus there. And that two-sphere must intersect the annulus because it separates the two components. So here's a picture of this annulus. This annulus fits between these two components. So I'll just put it over here to make it easier to see. And
I've unknotted it, but you can think of this two-sphere as representing that region between those two components of that link, the original knot and its push-off. And this two-sphere is going to intersect that annulus between them in some collection of curves. And one of those curves must run around the annulus and be parallel to the original knot. But that means that one of those curves lies on a two-sphere and bounds a disk. So there's a curve that's parallel to the original curve that bounds an embedded disk. So it's a knot. Right? If you have a curve on a two-sphere in R3, that curve is always unknotted. That curve bounds a disk on either side. So if you can separate those two components by a two-sphere, then you see a curve of intersection with the two-sphere, which tells you that each of those two components is unknotted. So it's not a difficult argument. So it wasn't observed, though, somehow. I've never seen this in the literature, but it means you never have to worry about boundary. Right? We're not going to have to worry about normal surfaces with boundary, because we're going to be looking for split links which have no boundary. So this simplifies quite a lot of the cases that Haken had to look for. So let's look at this split link problem. This problem was originally stated and solved by Horst Schubert, who wrote an exposition of Haken's work in 1961, which explained, which had most of the ideas I'm talking about today. It was very nicely written papers, and so most of the early references to the theory are to his paper. And he, in particular, gave the first proof of split link, first algorithm for split link in this paper. So here's the algorithm for split link. We'll take a link with two components, and we ask, does it contain a sphere splitting those two components? And the answer is, the algorithm is going to be construct all the fundamental solutions to the normal surface equations for the three manifold, which is the complement of that link, and then check whether any of them is a two-sphere which separates the two components. That's the algorithm. And unknotting is a corollary. So what do I have to do? To justify that this algorithm really works, what do we have to do? We know that given a finite simplicial complex, we can use the Hilbert basis theorem, and we can construct all the fundamental solutions to the normal surface equations. What we have to prove is that if there's a splitting two-sphere, then one of them is a fundamental normal two-sphere. That's the one thing we haven't done yet. Okay, so let's finish that off. And almost all of the three manifold algorithms are of this flavor. You set up a problem. There's a certain surface that guarantees that this problem has a solution one way or the other. There either is or isn't an unknotting disk. There either is or isn't a splitting two-sphere. And then the work goes to showing that if there is such a surface, then it can be found among the finitely many fundamental solutions. So let's see how we do that for the split link problem. We're going to show that if there's a split, if the link is split, if there's a two-sphere that separates the two components of the link, then there's one in the fundamental solutions. One of the fundamental solutions will be a two-sphere that separates the two components of the link. So what do? We start with let's say we had some two-sphere that separated the two components. It's going to be some arbitrary smooth surface, or PL surface. And the first thing we're going to do is show that we can make it normal. So we've seen a normalization process where we compress or boundary compress or isotop. And can that mess up the property of separating these two components? Well, isotopy and boundary compression won't be a problem. The problem is compression. If we do a compression, like in the picture at the bottom here, if we compress a neck of this two-sphere, is it possible that initially we separate those two link components, but after the compression we don't? Well, as you can see in this picture, when you do a compression, you may get you'll get two different two-spheres, but at least one of them will still separate the two link components. It's impossible for neither of them to separate the link components. There's a little homology argument that can prove that. Or you can do a little intersection argument. If you take an arc from one component to the other, it crosses the original two-sphere once. So that intersection point must lie on one of the two new two-spheres, so that one will also separate the two of them. Okay, so without too much problem, we've reduced our problem from general two-spheres to normal two-spheres, which I think answers your question about what topological properties are preserved. In this case, it was separating the two link components. But normal is not the same as fundamental. Right? You could have very, very complicated normal surfaces. We want to show that one of the very simple fundamental surfaces, which we've enumerated and can look at one at a time, we want to show that one of those will be a splitting two-sphere. So now we will use this is where we use a little three-manifold theory. Well, not too much. So Schubert proved this little lemma, which will guarantee this property. What we're going to do to find a nice separating two spheres, we're going to look at if we look at all the possible two spheres that separate these two link components, among all of those, we're going to take the simplest. And if you're a geometer, you might think the one that has smallest area. And combinatorially, it's going to be the one that has smallest weight. Of all the two spheres that separate the two link components, let's take the one that minimizes, the normal two-sphere that minimizes the number of intersections with the edges. And we're going to show that that particular two-sphere is fundamental. Let's call it V. And remember, fundamental means that it's not a sum of two other guys, that it's not, you can't write it as A plus B, where A and B are also normal vectors representing surfaces. So supposing V is not fundamental, supposing it is A plus B, so then Schubert said, let's write it as a sum A plus B in such a way that A and B, which each represent surfaces, minimize their number of intersections. So they'll intersect in curves. Let's minimize the number of curves of intersection of A and B. And Schubert says if we do that, then A and B will each be connected, and none of the intersection curves will be separating on both the surface A and on the surface B. So let me show you why those are true. It's just a little case analysis. So supposing that you had the minimal number of curves of intersection for A and B, and that A and B were not connected, were not each connected. So I've illustrated that here. A is the blue circle, it's connected, but B is not connected. B has a B1 component and a B2 component. But A plus B, remember the way to get sums is to do these exchanges along the intersections. So when you take A plus B, you'll get this connected two-sphere at the bottom right. But A and B do not themselves have to be connected. So Schubert says, well, if B is not connected, take one of the pieces of A, take one of the pieces of B, the red one, say here, and add that to A, and call that C. So then B will have more curves of intersection with A than C does, because when we added B to A, we got rid of some of those intersection curves. And so we can rewrite this, this vector V, the surface V, as C plus D, which have fewer curves of intersection.
So we can assume that that if you can decompose V, if it's not fundamental, then each of the pieces is connected. It's a sum of two connected surfaces. And this just shows how the tetrahedra might sit that force this type of intersection. And the second thing that Schubert showed was that if you minimize the number of curves of intersection in the intersection in A intersect B, then that curve has to be non-separating. That intersection curve, the green one there, has to be non-separating on one of A and B. So in the example I've shown here, it's separating on both. The curve on a two-sphere is separating. And that says that that couldn't be the most efficient way of writing V as a sum. And it's a simple argument, but let me skip it. It's a similar flavor. So now let's finish the argument that there's a fundamental two-sphere that splits the two link components. So we took a minimal weight two-sphere, and now supposing it's a sum of two pieces, we can assume they're connected. And because they're connected, and the Euler characteristic adds, and the sum of the Euler characteristics is the Euler characteristic of V, which is this minimal weight two-sphere. The Euler characteristic of a two-sphere is 2. So how can 2 add up as the Euler characteristic of two other surfaces? Well, the only way you can get 2 as the sum of two Euler characteristics is 2 plus 2. 2 plus 0. 2 plus 0. You can't get 1 plus 1 because we're in S3 and there's no Euler characteristic 1 surfaces in S3. And you only have two pieces, and all of the Euler characteristics are negative and none are bigger than 2. So 2 plus 0 is the only way you can add up to get 2 with two connected surfaces. And there's no Klein bottles there's no embedded Klein bottles in S3. So our only possibility is a sphere and a torus. Somehow a sphere and a torus are being added to get this new sphere, which is separating this new minimal weight sphere. Well, why can't we just use the two-sphere A instead of we started with what we thought was a simplest minimal weight two-sphere, and now we've written it as A plus B because we're assuming it's not fundamental. If A is a two-sphere, why can't we use that? Well, we could if it happened to separate the two links, but it can't because it has smaller weight. We started with a minimal weight guy, and the weights add, so A must have smaller weight. So the picture must be like it right. The two-sphere does not separate the two components. The union of the two-sphere and the torus separate them. Let me show you a picture of what it must look like. You see this picture at the bottom right here. Not that one. The picture at the top is what A plus B must look like. If you look at that picture, then A plus B does separate the two components, but the blue two-sphere does not separate them. And the torus does separate them, but you can't, a torus is no good. We're looking for a splitting two-sphere, so we can't use B. So it looks like we're stuck, but there's this operation you can do now using the fact that these curves of intersection must all be non-trivial on the torus because, remember, they were non-separating. They can't separate on both surfaces, and they separate on the two-sphere, so they must be non-trivial intersection curves on the torus, meridians. So we can use one of those. We can use a disk on the two-sphere to compress that torus and get a picture like this one at the bottom right. And when we do that, we actually do an irregular sum, not a Haken sum. We're going to get something that's not normal. It looks like one of these exchanges instead of the... So it does give us a two-sphere that separates the two pieces, but it's not a normal two-sphere. But no problem.
Now we'll just normalize it, reducing the weight even more until we wind up with a contradiction, because we'll get a normal two-sphere of smaller weight that separates the two components. So that was the whole argument. I really ran through it very quickly, but that was the entire argument for unknotting. So we now have seen how Haken's arguments, together with Haken's ideas, together with some arguments not completely trivial to show that one of the fundamental surfaces is a separating two-sphere, are enough to prove the unknotting theorem. So next time what I'll do is go off a little bit into differential geometry and try and connect normal surface theory to differential geometry and show how that leads to an algorithm to recognize the three-sphere. But I'll stop here for today. Thanks. Not that I know. I don't know if such an. I don't know anybody who studied that. Yeah.
Since there's some computer scientists here.
The question, by the way, was: does anybody know, or is there a notion of a random normal surface?
So since the space of normal surfaces is a union of exponentially many cones, so you could kind of cut those cones off at some height and then try and sample uniformly at random from those polygons. Is that easy to do?
So I think it's Saul's suggestion is one of the obstacles to doing something like sampling normal surfaces is you get different quad types. So first separate the problem into three, and randomly pick one of these 3 to the t quad configurations, and then sample from within one of those configurations. But I'm not quite sure how you do that. Yeah.
How do you like, well, just say total weight less than L, and I need to sample from a polygon. How do you?
If you're going to sample well, right, you need to know how many points there are in each of those 3 to t cones. And you don't want to enumerate all the points in each of those 3 to t cones because that's hard and there's lots.
Let's sample badly.
Yeah, Ben.
Yeah, so I haven't seen this split link argument where you double the knot and then look for a sphere, which is nice, right? So my question is, do you know if I give you a triangulation of the complement of a knot, say an ideal triangulation of the complement of a knot, is there an easy way to get from that to a triangulation of the complement of the double of the knot?
Right. So the question is, in these actual implementations of unknotting, they use ideal triangulations, which are, instead of using 750,000 triangles the way I set it up, they would use 3 or 4 for simple knots. So it's much better computationally. But the question is, do those types of triangulations somehow adapt to pushing off a copy of a knot and getting a 2-component link? And I haven't thought about it, so I'm not sure.
I'm happy for answer the same question with an ordinary triangulation with boundary, by the way.
Yeah, I'll give the same answer to you. Yes, Larry. Yeah.
Perhaps you would be willing, even at this early time, to tell us the history of publication of this famous problem of recognizing the three-sphere. See, I'm ancient and I have some memories of what was unknown, but I won't say.
So the question is, if I would say something about the history of the recognition problem and its publication. So I was actually present for most of it, so I could say a little bit. So I did, although maybe I should wait till after my lecture about the recognition of the three-sphere. But there's a really fundamental new idea in recognizing the three-sphere, which is the idea of an almost normal two-sphere that I'll talk about tomorrow. And it has some very beautiful connections to minimal surface theory. And this idea was introduced by Chaim Rubinstein, who gave talks about it. And he proposed an algorithm, which we now know works correctly, based on this idea. But you know, these algorithms have two pieces. There's a description of the algorithm, and then there's a separate argument why the algorithm does what it claims it does. So he outlined part 2, but never wrote the details down. Abby Thompson found a different argument for part 2, which was very elegant and much shorter than and clearer than what he was proposing, in my opinion. So
The date of this final Abby Thompson contribution, the date.
oh, when was it? It was maybe a year or two after he gave his lectures. I don't know the date. I think that the lectures he gave about this that we heard, both I and Abby heard, were in 1991.
I just remember a conversation with Haken in the 70s, I guess. So I remember it's time I got down to writing down an algorithm to recognize the three-sphere.
Oh, really?
Was a right problem.
Oh, yeah.
And,
Well, there was some published proofs which were incorrect, I think, well, withdrawn, yeah. There was some other arguments based on Haggard splittings. Yes?
How does prime knots, I mean, asking for primeness fits into this normal surface theory?
So you can try to recognize whether a knot is prime or not. And that amounts to finding whether the knot has an annulus in its complement. And the same techniques will work for that too.